Stretch a spring, bend a beam, compress a rubber block, every material responds to force in a predictable way. This unit gives you the language and laws to describe that response. The key question is always the same: how much does it deform and does it recover? Hooke's law states that the extension of a spring is directly proportional to the applied force, provided the elastic limit is not exceeded. F equals K times X, where K is the spring constant in newtons per meter. The spring constant K measures stiffness. A large K means a stiff spring that needs a large force for a small extension. A small K means a compliant spring. Beyond the elastic limit, the material no longer obeys Hooke's law, and the deformation becomes permanent. The limit of proportionality is where the fx graph first curves away from the straight line. Elastic deformation means the material returns to its original shape and size when the force is removed. The atoms are displaced but not permanently separated. Plastic deformation means the material is permanently changed. After the force is removed, it does not return to its original dimensions. Energy has been used to rearrange the atomic structure. The elastic limit is the maximum force up to which a material behaves elastically. Beyond it, plastic deformation begins. It is not the same as the limit of proportionality. The limit of proportionality comes first. Stress is the force per unit cross-sectional area. Sigma equals F over A, measured in pascals. Strain is the fractional extension. Epsilon equals X over L, a dimensionless ratio. The Young modulus E is stress divided by strain. It describes how stiff a material is, independent of its dimensions. A high Young modulus means a stiff material like steel. A low Young modulus means a flexible material like rubber. The Young modulus is the gradient of the linear region of the stress-strain graph, before the limit of proportionality. Beyond that point, the graph curves and the modulus no longer applies. When you stretch a spring within its elastic limit, you do work on it, and that work is stored as elastic potential energy. The energy stored equals the area under the force extension graph. For a spring obeying Hooke's law, that area is a triangle, so the elastic potential energy equals 1/2 times F times X, which is also 1/2 kx squared. If the material is stretched beyond the elastic limit, energy is lost as heat during plastic deformation. The area under the unloading curve is less than under the loading curve. That difference is the energy dissipated. Think of Hooke's law as the foundation: force proportional to extension, spring constant K measuring stiffness, all valid only while the material stays elastic. Once you cross the elastic limit, the rules change permanently. Stress and strain scale Hooke's law up to any shape or size of material. Their ratio gives the Young modulus, a material constant that tells you how much a wire or rod resists stretching regardless of its dimensions. The area under the force extension graph always means energy. In the elastic zone, that energy is stored and fully returned. In the plastic zone, some of it is lost as heat, and that loss is exactly the gap between the loading and unloading curves.